take. Hi guys, I'm Soham. To surface, I was in a team, but I did much of the project alone. So I wanted to do the presentation and then show you guys what I learned. So I did project 3, which is leakage attacks and mitigation, specifically for SEAL and Path-ORAM. So the core question of my topic was basically how do different leakages actually help an adversary? I think having the SEAL and then the project Path-ORAM is like important, but the main question is definitely figuring out like what kind of leakages are happening, as well as what kinds are acceptable. So I tried making the 7-slide requirement, but I have this extra slide because I thought this was important, as well as 3 slides for my the plot that I have. Hopefully that's fine, and then one more for thank you and the intro slide. So the problem definition is we have 2 attacks. We have the first one is query recovery attack, and then the second one is database recovery attack. In query recovery, what we're trying to figure out is given like the data set, the padded data set, as well as the query volumes, can we figure out what query was done and can do so better than random, which is important. And then database recovery attack, given the volume, the ORAM identifier, which is like which ORAM was accessed from the database, as well as the padded data set, of course. We return the encrypted tuple, and we are basically showing can the adversary map each tuple back to the plain text keyword that we have. So I guess what's important to know is that this is very strong attack. The known data here, I think I cover that in the next slide, but the known data here is quite a lot, and in the real world this wouldn't be the scenario, but we are considering these attacks to show what might happen, and then to show what is the security still of SEAL and Path-ORAM. So using these queries, the question we're asking is, what is the success, or how many queries and tuples the adversary correctly identifies? And the goal of this is to compare different parameters in SEAL, because SEAL has 2 parameters, alpha and X, where X is for padded, and I'll cover what exactly those parameters mean for the leakages, but just for now, just to know that we are trying to compare different parameters with our data set, as well as show the success, or like what the success would look like, is we should be able to figure out where exactly SEAL and Path-ORAM are strong and where exactly they're weak, right? So that is the point of the experiment. Yeah, so that's fine. So the threat model. Okay, so what does the client know, and what does the adversary know, and what is he trying to figure out? So the client wants to store his encrypted database on an untrusted server and issue like keyword search queries. Keyword search queries are where you're given like a word, so it's a word, and then you get back all the documents associated with that word. So the server executes these queries and returns results without learning their plain text context. So even though the QR and DR attacks have the tuples, or they know what is encrypted. We do not want in the real world to, we do not want them to have that information, and we are under the assumption that in the worst case scenario for these attacks, what's happening, like I said before. So the server is the untrusted party that observes communication between client and the server, right? It can do 4 main things. I think I should have switched these, but it can observe the volume of the tuples returned, so like the volume leakage. It can know the size of the number of documents returned, and this is important for the QR attack. It can observe which of the ORAM bucket was accessed, right? And this is basically where SEAL comes into play, where we'll cover the whole idea of SEAL. Known data is the plaintext frequency distribution of the database. This is the powerful assumption. The known data is this is something that like the professor says will be laughed upon if we wanted to show that this is the real world. Fourth, observe the full sequence of queries over time, right? It knows it can observe what the client is querying, and then we want to use that information for these attacks. One, what it cannot do, cannot do. Yeah, so what it cannot do is it cannot decrypt the queries. That would go against the point of what we're trying to show. It cannot decrypt the queries. It cannot learn the PRP key. This is important, and this is something I had it the reverse way, where it did know this, because one of the assumptions we're making is it knows which of the ORAM bucket, or like the ORAM identifier, and the PRP key is not only used for that, but it's also used for this. But I have 2 different PRP keys. But it cannot even only know the PRP key for this, because keys are secret. It cannot see what specific document was accessed in the ORAM. So it cannot know the document ID, it's encrypted, because knowing that can get more information in these attacks. And it cannot actively interact with the data. It cannot send queries itself. It cannot change data. It cannot just mess around with the data. It can only observe. It's a passive adversary. We defined these attacks before, but only the difference is that between query and database is that database has this, which I just. Okay, so what is the approach? Just to get something out of the way, the server is very dumb, so it's just a storage system that has the ORAM tree, which is encrypted, or in the version that I'm doing for Path-ORAM. But yeah, let's see the stuff now. So I couldn't fit all the information within the slides, so I just wanted to show this, and this is a much more interactive way that I think of doing it as well. So let's go. So let's do Path-ORAM first. So in Path-ORAM we have a tree, right? We have a tree, and we have this side is in the server, and that side is in the client. The client stores, in the version I'm doing, the position map as well as the stash. If you're doing recursive, we just need to store the position map, and if you're doing recursive, we don't have to store the position map. But in the version that I'm doing, we didn't need to go for efficiency. I just wanted to see and play with Path-ORAM and SEAL. Again, the main question is leakages. So the version I did was just the Path-ORAM, right? And I'll talk about the results after. So in Path-ORAM, what we have is, let me just look at my notes real quick. Where do I want to start with? So what is the position map? The position map is, okay, the version I have, it's a dictionary, but I don't think I need to cover like how exactly this stuff is. So I'll just cover the bigger picture, which is I think is what they want us to do. And so all of this is untrusted, and all of that is trusted. Okay, let's say the client, all of this information is also encrypted, and this doesn't need to be encrypted because the client side is trusted. So let's say the client wants to query for 5. What is that? How does that process look like, right? He wants to get the value of 5. So it looks at the key, right? The keyword. So these are all keywords, right? The 5 is keyword and 4, 3, 1, and 10. And each of these have like buckets. So you can have something like you can have multiple sort of information within each of these buckets. And what we have is, for each keyword, we're mapping up where exactly is it in, right? And so this might be just one of the keywords called 5. And we want to figure out where exactly that all of the elements for this are. So in a structure like this, depending on the bucket size, as well as the length of the tree, we can have, let's say, n is the length. We can have 2n, because it's a tree, 2n nodes and 2n times bucket size. So we can store that many keywords, depending on what our n is, or the depth of the tree. So to just simplify this, let's say we want to get out 5, I can just keep it like that. So what do we see? So first, the position map, the client checks the position map, and it figures out the leaf node. This is 0 indexed leaf node, so 0, 1, 2, 3. So it figures out, okay, so I need to grab 5, which is my second leaf node, right? And it knows that this is the root. So what it does next is that it figures out, okay, I need to transverse this line of it, right? And you go here, here, here. And so the first thing it does is then it adds this element and any other sort of elements in this to the stash. So let's just assume that everything else is a dummy block. And so it adds 4, it adds 1, and it goes here, and then it goes to the 5th one. And so it gets all of these values in, and then let's say they're dummy blocks, but depending on that, it fills up the stash. So that's the process of the query, right? And then now when all of this information is going to the client ignores the dummy blocks and only puts the real block elements in the stash. And one of the important things is it also either it can recompute how many elements that it accessed by just looking at the depth of the tree and then times the bucket size, or it can like keep track of it as an index, like integer that I did. Then, given the stash, it can then when it gets all the information streamed to the stash, it can decrypt it and then figure out when we pass this 5, what are the associated. We're passing also information of the value B1, B for 4, B for 1, B for 5, and it figures out what the value for 5 is, and it can use that information, right? And then so that's the process of read. There's also eviction. Let me cover that before I go to write. So now what it has to do is that it has to figure out, or it has to then randomly reassign 5 to a different block. Let's say it randomly reassigns it to 0. It updates that position map to be 0. Then it looks at the stash, and then from the bottom node, let's say there was another element here. Let's say it was 10, and then there was also 5. So now it has 10 as well. Just ignore the order. Now it has 10. So it goes to the bottom part of it and checks, okay, for the fourth element, can I put this here? And it checks what the node for that is. It's 1. No, I cannot put this here. I need to go 1 level up. Can I put this here? It sees, the reason it cannot go here is because there's only 2. Then it sees here, it says 2 and 3. Then it reaches the top node, root node. It doesn't have to check anymore because it knows that it's all, and then it can just put 4 there, right? Then for any other elements, it can do, for 1, it can see if it wants to put put this here. It cannot put this here. It checks for here. This is mostly empty, so it can put this here, right? And for 5, because now 5 is not to 0, we cannot put this here anymore. We go 1 level up. We can not put this here anymore. We go 1 more level up. We can put this here if this was not full, right? If this was, let's say, full with other elements in here, then we will keep that element in the stash and then move on to the next element. And for 10, we see that it is still 2. In the position map, there would be a tile point of 10. It is still 2, so we add it to the last block. The reason why we want to do it from bottom up is that we want to be greedy and we want to push elements as far down as on the line as possible to keep the root node as uncongested as possible. Right, so that is the process of read. Okay. For write, it's very similar. The process of going down the tree is similar, but let's say now we want to add. Let's say we wanted to add 10, right? So we read 2. We wanted to add 10, and we wanted to add it to leaf 2. So we read all the elements here to leaf 2, and then we pushed everything to the stack, right? And now we want to add that 10 to the stack. And then as we're evicting, we add the encrypted value of 10 to the ORAM tree, as well as we want to also in both read and write be adding dummy values so that we do not want to, let's say we had 4, 8, 12. We had 12 reads. We do not want to add more than 12 or less than 12 elements. We want to add 12 elements exactly and then stop with the cache. Okay, so that is how we do this. So that's the high-level idea. I think explain the high-level idea, the intuition behind it, and how it addresses the problem defined earlier. Visualizing your solution will make it easy. Okay, so next we can also go to SEAL, and we can show how SEAL is built on top of this. So SEAL has 2 main introductions, as well as some helper code that combines these introductions and these things into SEAL. But the main 2 things are adjacent padding and adjacent ORAM, right? So adjacent padding is basically when you're given the data set and X. The data set here is the complete data set, which are tuples of keywords and document IDs, so all the IDs for that one keyword. And X here is the amount you want to pad, right? You want to pad the n data set, if the data set size is n, to X times n. And so how you do this is that you go through all of the keywords, and for every element, you check what the count of that element is, and then for what the count of the doc IDs are, and figure out what the next 2 to the a power after the count is, right? And then you pad that many more dummy elements to the keyword. You do so for all keywords, and then you return the data set containing all keywords. For a JSON ORAM init, the thing you're given is M and alpha. M is different here from the data set because M is like a sorted tuple list which contains word, comma, doc ID. So it will have like word, comma, 1, word, comma, 2, word, comma, 3. So it has the same word and then all doc IDs, and it's a sorted list, right? So what my implementation differs here, and I will go over that in my implementation details, but the pseudocode for SEAL creates 2 to the alpha arrays of n to the 2 alpha size. Basically, that cancels out, and that's just all of the array sizes are now n, or like combined are L, n. And then for each element in M, what it does, it takes the PRP, which is a pseudorandom function, pseudorandom permutation, and then it takes the element, it puts the element inside that function, and then it takes the first alpha. So if alpha is, let's say, 1 bit, then it takes the first bit of that, and then for that array, so if you can assume array to be L, so for L1, it will then put at position the remaining bits. So if it's like a 10-bit PRP, and the PRP is very strict on how many bits it outputs. The remaining bits are what is used for the position in the array, as well as then that position is given a value, right? And after we do this for all M elements from 1 to n, we initialize all the arrays using just the Path-ORAM initialization, given like the size as well as all parameters. And then we return all of these, which is then used for access. Access is very simple. Access needs the same PRP, so a PRP with the secret key. That secret key is not given to anyone, so no one knows. And then it uses that PRP to get get the string again, and then use the alphabet. So whichever, like let's rewind to when we said it was 1. So it uses that 1. So it checks the first ORAM if it's 1 index, or the second one if it's 0 index, and then it checks that element using it queries that that remaining one to the ORAM to get back the return value. Okay. So how does this address the problem defined earlier as well? So I explained my intuition, explaining the high level of the design. How does this actually talk about the idea of figuring out what kind of leakages are acceptable, right? So as you can see in Path-ORAM is very strict in the sense that we do not leak any information for the 2 attacks that we mentioned, given the data shows it's kind of different, but it reveals very less information given those 2 attacks, because in SEAL we are dividing all of the arrays into alpha, or 2 to the alpha arrays, right? So we will the adversary will know which ORAM you're accessing, and so you can figure out what are the first alpha elements of that, right? And so we should see in our graphs that the more alpha, or the more bits that the adversary knows, the better it is at predicting what tuples, or what the right keywords are, so database recovery, right? And then the other part of it is that for the query recovery attacks, we also know the padding, right? So if the attacker knows the volumes, it also knows what It also knows the volume of the query done, so like the resulting volume of the query. So it can then map out for specific values. Let's say there was only one query that returned 10 document IDs. Then it can map out that and figure out, okay, what keyword was it, right? So it can recover the query recovery attack. So yeah, so based on this, you want to figure out how does Path-ORAM and SEAL compare within leakages. So that is how we are addressing the problem earlier. Okay. Implementation. As well as engineering decisions. So, what are our files and what did we use to do so? So, the main thing that we had were these 4 files. There's also load data, which loads data file. But the main 4 files are client, which is our Path-ORAM, client seal, which is the black box seal on top of our client, client simulation, which is pretty important, and it's basically a simulation that instead of seal having to go and actually grab all the data and do all of the going down through the path trees and then evicting, we just skip that step and then give out what we want for our attacks. And then main.py, which has these 2 attacks, as well as different experimentations that I did. And this is the interesting part of it. This is where we're answering our question. Okay, implementation details. Okay, so what exactly was it? So in client.py, what we have is, we have alias GCM, which is our encryption scheme, which creates our PRP or CPA secure function, as well as creating the nonsense, so the nonsense and then the PRP to ORAM bits that we have in client seal. The other thing that client.py has is it has the position map, the stash, and oblivious read and write functions. So the way we do read and write, if you look at the code, it seems a bit weird because we have functions called read and write, but the only time we're calling the server is in our retrieve from server path, or and then in the end of that, we are also doing eviction, where we write back to the server, right? So we in both of read and write, we are doing one retrieval and one write back, one eviction. Okay, so this has the okay, so we went over, okay, and we are also doing this in Python, which is our programming language. I explained the tools that we use, as well as the libraries and frameworks used. We can cover all for them for all, and then we can go to our engineering decisions. So the next thing is client seal. Client seal is a wrapper on top of Path-ORAM from client.py, and it has an initialization function which calls which does ADG padding as well as ADG ORAM initialization, and then it calls the ORAM initialization as well, like we saw before, and it has one access function, which is basically what the ADG ORAM access does, right? And so what we have is a O dictionary that gets back the starting index as well as count for a keyword. So the O dictionary is something I think I didn't explain in the seal, but basically, if you remember the array M has multiple keywords, right? So each keyword is starting at a different index, and each keyword might have, like, let's say 10, 12, 15, or unknown amount of elements for that keyword. So what ODIC does is that it stores the index as well as the count of of all keywords, and then we also store this as an additional ORAM in SEAL, right? So this is one more ORAM that we have to store in SEAL, and so all of the information is also encrypted within this ORAM. Okay, so we covered object, and then client simulation. So like I mentioned before, actually doing SEAL is very expensive because you have multiple ORAMs. Even doing Path-ORAM is very expensive for the amount of data we have, because our data is in the millions, in the 100,000 range, sorry, as well as the number of queries we have. Most of my experiments were done with 1,000 queries, so so that is something that we took into account. And so we created client simulation, which basically skips these ORAM operation and instantly records which ORAM bucket each index maps to, and uses that for our evaluation. Next, we have main.py. Here's where I did most of my experiments, and this was what was used to answer all of my questions. The things we have here are our two attacks. So we have our query recovery attack and our database recovery attack in this. I can also show the code for how that looks like, as well as we have all of the experiments or simulations that we did. Let me show you. Let me go to another slide, and then I will show you all of the stuff. So here are our experiments / results. So for the data sets, we used the TCPH and Chicago crime data set. That is the same one used in the SEAL paper, and we used TCPH as well as with the scaling factor of 0.1. And then we also I also did another data set which I was interested in, mainly for database recovery. Apartments also has 22 attributes, the same as crime. And crime TCPH has different TBLs with different number of attributes. So I also list that in my code. Okay. And then metrics for the experiments I'm going to show you are just 3. There are I do not want to go over the 7, as well as I was already going way over time. I think I have like 15 minutes plus. Or 20 minutes plus. So I want to just show you 3 of the experiments that I had, as well as just mention some of the other things I did. I checked out uneven padding numbers, which didn't give me the results I hoped for, because I was imagining if there are uneven paddings, the query recovery attack will be different. Then I had, but I think I used way less number of paddings to know a noticeable difference, because the data sets are so large as well, right? And then the other thing was that I was also thinking, I think I include this information in my read. So let's move on here. Convergence of simulation SEAL as well as actual SEAL. I did not include the proof that the simulation SEAL is the same as actual SEAL, but you can look at it in my slide, in my code. And there's images called convergence, basically. And then we also can show database recovery attacks over different attributes for different alpha and different X. The only attribute I'm doing right now, the one I'm showing you right now, but I've done more, is is in crime, I think, and it's the attribute 5. Can't remember on the top of my head. what it exactly represents, but yeah, it was one of the good ones. And yeah, I basically did my experiment in 3 different phases, and each phase had more experimentations. Describe this experiment setup. So, oh yeah, I gotta describe the experiment setup. Okay, so this one. Let's do this experiment. What was the setup for this? In this setup, we had an axis over database recovery over number of alpha as well as different x's. Because remember, in database recovery, what we care about is both the alpha bits as well as the greedy bits, right? And so, as you can see here, we have this is only for one attribute, attribute 5. So the greedy is pretty consistent, around 20%, and anything less than greedy is showing that it works, and then anything above greedy is showing that it's leaking way more information. So as you can see, for x equals 1, which is basically our Path-ORAM, and then also alpha bits 0, we have something like around 12% database recovery, and then for still x equals 1, but with more alpha bits when you go into seal, we have more leakages in database, right? So again, this means that it's able to recover more tuples from the total stuff, right? And then we can see some interesting stuff. We can see in 32, it kind of zigzags across. So this could also be because of the number of queries. 1,000 queries are still higher than 100, but they are still less than 10K. But I don't have a beefy computer. That was what I had. So 1,000 definitely gave us good results that we wanted to see. So this spike might just be because of that. And I guess if I had to make a recommendation, I would see that maybe 12 alpha shows like the least shows the biggest dip in a while, as well as depending on the amount of leakages you want, you can go from 4, 8, 16. I would also put in 32, even though it's higher than these two, and then 64. I guess for higher ones, I would just go with the 8, right? And then this is for the crime data set, as well as in TCPH. I didn't do my apartments in database recovery for it. I did do it, but not in this one. I don't know. For this one, I just was recreating seal, bit of seal. And then for a TCPH, I would definitely recommend going with a higher alpha, like 20, and then doing, this one's for orders, which has 9 attributes. So I might go 8 as well, and maybe different conductions of this showed a big dip in 20. So it might be useful to go 20 as well as 8 again, padding. Again, the more you pad, the more the data set grows, and so the more time it takes to calculate queries, right? Because the trees become larger. So I would go with 8 in that as well. That's a good thing. Okay, next. Query recovery attack for TCPH orders. This is an interesting graph because we are now, instead of doing, we don't need alpha information because alpha information doesn't affect query-based attacks, query recovery attacks. So we are doing it across all attributes, and this is 0 to index. The seal paper does it in 1 index, but that's it, whatever. And then orders are from 1 to 9. So it is interesting here to see why 2, 5, and 7, or in SEAL it would be 3, 6, and 8 spike, and that is because the amount of unique values for 2, 5, and 7 are very little. I think it was something like 2, 5, and 1. Yeah, in 7 it's 1. That's why you see all of them. Like because it's just one, it can one keyword. It can basically guess that one keyword, and so all the spikes go pretty high. And so most of them is baseline performance. Nothing is really good at 2, so I might go higher padding than I did with 16. I think I can show you the other ones that I did, but I do think for 2 it is pretty close enough, and it's not giving 100% for your recovery, so that is something. And then for attribute 5, you can see that anything except no padding, and no padding here basically means that it has, it's basically Path-ORAM. So it has no padding and it also has 0 alpha, whereas for these ones I did give it some alpha, like 2, I believe. And then, so Path-ORAM has that leakage, and for 7, nothing works. Next thing I did was, one of the most recent things. This was very interesting for me because I was looking at joint recovery attacks, which is one of the things they do, as well as range. So in joint recovery attacks, what we see is that, again, for alpha bits, 0 as well as no padding. So here we see that it's pretty below the greedy strategy. And this one was, it was for supplier and nation. Attribute 7, I think, yeah. So the nation name. Yeah. And so no padding, as well as that gives us that, but we can see that if we continue to have no padding, and we go up in the alphabets, we get a lot more leakages, right? And this was what we see in SEAL, that this is like an exponential growth. So the more alphabets there are, it exponentially leaks more information, whereas these are much more calmer in comparison to no padding. So this definitely shows how much padding can affect alphabets. And I think I'm talking about decisions and signs. So yeah, insights. So we can see, like, the recommendation I would make here is that I would choose. I think for alphabets 0 to 10, a 2 padding is very good because it consistently stays under. But I would also maybe go with 4, depending on how much time and storage that you have, right? Like how much latency you can accept, as well as how much storage you can afford. Yeah. Alright, that is the end of this. I will, depending on, I tried to cover everything, and I tried to cover it under the time as well. But depending on how this goes, I will show you the code or I will remove it. Let me just show you the code. It's definitely above 7 minutes. Yeah, okay. I'm sorry about that, but my code has a very good documentation as well. My code has a very well developed README, which includes like the files, implementation of what the query recovery attack is, what the database recovery attack is, Path-ORAM SEAL, SEAL simulation, and all my files also contain documentation for all of the things I did, and then it also contains the 3 generations of simulation that I did. You know, I did first simulation. I did more above that, but I called this 0 because this was the genesis of everything starting to work. Then I show my simulation equivalents. Then I show my second gen ones that I have right now, and then I'm developing the third gen, which are AI ones, which is pretty interesting. And I have my clients. I have how to run this. I have the questions I asked to Apostolos, as well as fun things I'm going to try next. And it has so many PNGs. It has a bunch of DR apartments x0, x2, so for different paddings over attributes. Yeah, I just get so excited. I'm just going to show it to you. So for different attributes and different paddings, so in this one I did 8, and then for different alphas, what does that graph look like? This was pretty interesting. One of the interesting stuff I like about mine is I did the convergence plot, showing that simulation and the actual seal are pretty consistent, right? Especially for query recovery. Query recovery shows that as we go to higher orders, and that's also informed my decision of number of queries. At 1,000, I was already seeing pretty good simulation and pretty good database recovery. If I went farther, I was because 10,000 took so long. I was also trying under 100,000, which is I think one of the recommended ones. But as we go farther, it takes longer and longer time. I think for 10K, it was like 2 hours that I had to wait for it to finish on just this one plot. I think I showed these in their crime. These are the apartment tests that I did. This is the supplier nation. I also tried the uneven ones that I was talking to you about. Let's say for uneven paddings, how does it affect the outcome? And here I did something stupid. One is basically no padding. So I just did it. I did it twice. But I could also do 7, 12, 15. And then that was my first one. Yeah. Thank you again for listening to me. I'm going to just move back here. The seal is a pretty nice addition.